Today in linear algebra we have a slightly more interesting theorem. Basically it says that if V1 and V2 are subspaces of a finite dimensional vector space, then the dimension of V1 plus V2, so the sum of these two subspaces equals the dimension of the first subspace plus the dimension of the second subspace minus the dimension of their intersection. And this kind of looks weird at first, but it actually makes like a lot of sense. For example, if we try to first just see the intuition, if we draw a 3D plane, this is a 3D plane. We got the X, Y, Z axis. We can basically, imagine. Let's, just to get some intuition. Let's imagine we have a 2D plane here. So we have like a 2D plane that spans the XY axis. It spans the whole XY axis. I'm just drawing it like as a square. And then let's imagine we have a 1D plane, so a line that spans the z, and imagine we have a line that spans the z-axis. So and the combination of these two basically gives us all a 3D space, because we can imagine that we're moving this green. We can imagine that we're moving this green plane, up and down. Let me just like this whole thing. We can imagine we're moving this whole 2D plane. Okay, just imagine moving this whole 3D plane up and down this line. This 1D line, and with that we can basically we can engulf all of the 3D space. And the dimension of this plane, the green plane, is 2. The dimension of the line is 1, so equals 3. We get 3D space, and their intersection is just, they only intersect here at the 0 vector. So the intersection is 0, so minus 0 still equals 3. But now, if we imagine, if we have a second, like in a 3D space, now we can imagine if we have two planes. Basically, what happens now? Again, we have X, Y, Z. Now imagine that we have a 2D plane that goes here. So, bang, on the XY plane, and now let's imagine we have another plane that is on the ZX axis. So it's kind of hard to draw this, but so imagine we have a plane on the ZX axis now, and these two planes, again, we can move the green plane like up and down on the Z axis, but we can also move the plane on the ZX axis. We can also move this plane like left and right along the Y axis. So basically we get multiple ways to span the 3D space. And this still spans 3D space, but the dimension of the first plane is 2, the dimension of the second plane is also 2, and the dimension of their intersection, well, is just 1. So we get 3D space. The intersection between two planes is always just a line. So we have a plane here, we have a plane here. It's kind of hard to draw this, but they always intersect in a line, and a line has one dimension. So we get 2D plus 2D minus 1D, and that equals 3. So again, two planes also span 3D space, but they have some intersection. And here the intersection is a line. So this is why we need this term here, and this is why this kind of makes sense. The dimension of the sum is just the dimension of each thing minus their intersection. Here with the line and the plane, the intersection is 0, and here with two planes, the intersection is 1. And in both cases we get 3D space. Now, how do we actually prove this theorem? Well, because this is this is kind of analysis of linear algebra. We gotta prove everything. So basically, we can say that since V1 and V2, so the intersection between these two subspaces. Imagine we have like two subspaces here. This is their intersection. This is a subspace, and we have theorems saying that for every subspace we can find the basis. If we have a subspace, we can find there. If we have a subspace, there exists a basis for V1 and V2, and we can say that this basis, we can say that this basis is V1 to Vm. These are the basis vectors of V1 and V1 of this. I just say n. These are the basis vectors of V1 and V2. And now we have another theorem saying that if we have since we know that V1 and V2 is a subspace, and of a bigger space. Like for example, this is a subspace of, this is V1, this is V2. So V1 and V2 is a subspace of V1, and it's a subspace of V2. And we know that if we have a basis for a subspace, we can extend that basis. So we can add vectors to that basis to give us the basis of the whole vector space. There's a theorem saying that. So any basis of a subspace can be extended into a basis of the full space. So basically, we don't know what these vectors are, but we can say that there exists some vectors. Let's say u1 to uj. We don't know how much of them there is, but we can just say there exist some vectors u1 to uj such that the vectors v1 to vm and u1 to uj, that these vectors are a basis for the space v1. We can find such vectors u1 to uj such that this is true. And now, since v1 and v2 is also subspace of v2, we can also say that there exists, so there exist some vectors here. We can say that there exists some vectors w1 to wk. Again, we don't know how much vectors there is, but we can just say, to generalize it, we can say there's k vectors such that v1 to vm and w1 to wk, that these vectors are a basis for v2. This is true. Using previous theorems in linear algebra that you usually learn, we can find such vectors that this holds. And now basically, we want to, and if we check the dimensions, so here we have m vectors, so we can say that the dimension of v1 and v2 equals m, because we have m basis vectors. Here we can say that the dimension of v1 equals m plus j, because we have m basis vectors, we have m v basis vectors, and we have j u basis vectors, so the dimension is m plus j. And for this one, for v2, the dimension of v2 equals m plus k. We have m v basis vectors and we have k w basis vectors. So let me draw this a bit nicer. Write this a bit nicer. M plus k. And now basically we wanna what we're trying to prove now is that v1 to vm to u1 to uj to w1 to wk, we want to show that these vectors are a basis for v1 plus v2, because once we show that these vectors are a basis for v1 plus v2, we can we can easily we can prove the theorem, because if these vectors are the basis, then we say that the dimension, we can say that the dimension of v1 plus v2 just equals m plus j plus k. Here we can see, we have m of v basis vectors, we have j of u basis vectors, and we have k of w basis vectors. So this is the dimension, and we can do some algebraic manipulation here. We can add an m, so we get m plus j plus m plus k minus m. We just added an m and subtracted an m. So if you do this, we still have m plus j plus k. But now we know that the m plus j is the dimension of v1 and m plus k is the dimension of v2. So again, this equals dimension v1 plus dimension v2. And what is m? We said that m is the dimension of v1 and v2. So minus dimension v1 and v2. So dimension v1 plus v2 equals exactly this, and we proved the theorem. So if we can show that these really are the basis vectors of v1 and v2, then we basically proved the theorem. So basically, how do we show that they're basis vectors? Well, we got to show that we can say that these vectors are basis vectors if they span the space v1 plus v2 and if they're linearly independent. Well, the first part to show is really easy, because these vectors v1 and v1 to uj span the space v1, and v1 to vm and w1 to wk span the space v2, and all of these vectors are contained in v1 and in v2, and they span the space v1 and they span the space v2, so they also span the space v1 plus v2. So this part's easy to check. Now the slightly harder part to check is that they're linearly independent, but it's also not that hard. It's kind of weird how we do it. We do some again just some algebraic manipulation. We kind of mess around with the vectors. So basically, the classic way to show that some vectors are linearly independent is to show that if these vectors sum up to the zero vector, that the only way they sum up to the zero vector is that if all the coefficients are zero. So the only linear combination that gives us the zero vector is the trivial combination, and the trivial one means that all the scalar multiples are zero. So basically, we want to show that if so we want to show that v1 so we want to show that we can just call it random coefficient. So a1 v1 plus this is just a list. That goes a2 v2 plus a m vm plus, and now we can name the second one's b, I guess. b1 u1 plus bj uj, and then plus now we just add the final vectors, which are w, and we can name it wait, what did I name it before? Let me just check my notes. Oh yeah, c. So plus c1 w1 plus ck wk equals 0. So this is this combination of vectors gives us the 0 vector, and now we want to show that all a1 to am and all the b's and all the c's, that all of these equal 0. If we show that, then that means the vectors are linearly independent. And now there's a smart way we can do this using some dimension analysis, like some vector space intersections. So basically we can put all these vectors, all these v and u vectors to the other side. So we can say that c1 w1 plus ck wk equals negative a1 v1 minus am vm minus b1 u1 minus bj uj. So we just put all the other vectors on the other side. And now what we can see here, well, we can see that we know from before that all the vectors v1 to vm and u1 to uj, they span the space. Look, we can check when we set it. So all these vectors v and u, they're basis for v1. So all these vectors v1 to vm, u1 to uj, they're the basis for v1. So we know that this vector is gonna be an element of v1. But we also know that w1 to wk, these vectors all fulfilled our basis for v2. So we know that v1 to vm, they're basis for v1 and v2, and we added the w1 to wk vectors to fill it for a basis for v2. So we know that all of these vectors, w1 to wk, all of these vectors have to be in v2, because we use it to fulfill the basis for v2. So what we basically know is that this vector has to be an element of v2, because it's just the w vectors. But if these two vectors equal each other, that means that this vector here actually has to be so I don't know, we can call this vector like g, I don't know. So g has to be an element of v1 and v2. We can see that easily here. But now here the trick we can basically do is that basically wait, let me just check my notes real quick. Yeah, so basically this vector is a v1 and v2. So now what we can do is we can write the c1 w1 plus ck wk. We can write this vector in another basis, because we have a basis for v1 and v2, and the basis for v1 and v2 are just the vectors v1 to v they go to m, right? So v1 to vm, this is these vectors are basis for v1 and v2. So we wrote this vector. This vector describe this linear combination of vectors describes the g vector in basis v1 and v2. But we can also write this vector using the other basis. We have another basis for v1 and v2. Basically, what we're saying here is that the w vectors are basis for v1 and v2, and the v's are basis for v1 and v2. So we can write the same vector using another basis, using the v basis, but it's going to have some other coefficients. We can say that the coefficients are d. So d1 v1 plus dm vm. And also if these two describe the same vector, that means also k and m have to be equal. But basically could be if they're both the basis, the basis has to have the same dimension as the space. So but yeah, basically this vector here, we can also write it using the other basis vectors. And now kind of the interesting thing is, but the c and the d coefficients can be different. They don't have to be the same, because we have a different basis for it. But they still, this describes the vector g, and this describes the yeah, this describes vector G and this describes vector G. So basically we wrote G in three ways. This way, this way, and this way. But basically now if we subtract all these vectors, so C1 W1 plus CK WK minus D1 V1 minus DM VM, so we just subtract this side, we get that this equals 0. But here the beautiful thing is that we can see we have vectors W1 WK and D1 to VM. But as we saw before, vectors V and W, here vectors V and W make up a basis for, wait, what do we say here? Yeah, vectors V to W here make up a basis for V2. And if these vectors make up a basis for V2, that means they're linearly independent. Because all the vectors V1, all the V and W vectors make a basis for V2, that means they have to be linearly independent, which means, and we know if some vectors are linearly independent, the only combination, the only linear combination of vectors that gives us the 0 vector is the trivial one, which means all the scalars have to be 0. So we get that C1 to C, we basically get that all these coefficients are 0. So we get that C1 equals all this equals CK equals D1 equals DM equals 0. So basically all these coefficients equal 0. That's the only way this is possible, because if they're linearly independent, which we say that they are, they are because they're basis, these coefficients have to be 0. So now, basically, with our long equation here, we know that all of these C coefficients have to be 0. So we're only left with the V and the U vectors. So we have that A1 V1 plus AM VM, and then we get plus what are the other vectors again? We have we're using B, right? Yes, plus B1 U1 plus BJ UJ equals 0. So this is what we're left with. But now again, vectors V and U make up the basis for V2. So all the V and U vectors also have to be linearly independent, which means that all these coefficients, A1 to AM, B1 to BJ, all of these coefficients have to equal each other, and they all equal 0. Because again, all the V and U vectors make up a basis for V2, so they have to be linearly independent. And so the only combination that gives us the 0 vector are if all these coefficients are 0. So basically we showed that all of the A coefficients, I'm just going to write A, but these are all the A coefficients, equal all the B coefficients, equal all the C coefficients, equals 0. So basically what we showed is that this, the only way to write this, so the linear combination of all these vectors, if they equal the 0 vector, the only way this can be true is if all the coefficients equal 0, which means they have to be linearly independent. So we show that all these vectors span V1 and V2, and they're all linearly independent, so they indeed are a basis for V1 plus V2. And now again, as we already showed before, because they're basis, and we can say the dimension of V1 plus V2 equals m plus j plus k, because we have mv vectors, ju vectors, and kw vectors, and we can just add an m and subtract an m, and we know that m plus j is the dimension of V1, m plus k is the dimension of V2, and m is the dimension of V1 and V2. So we show the theorem, this holds, and yeah, that's it. That's how you prove it. It's a pretty useful theorem. We got the geometric intuition. It makes sense. So yeah, thank you for watching, and that's it. Sorry if I was kind of all over the place. It's actually pretty confusing. Like, this is a pretty long theorem.